Mm-hmm.
How does that play into account?
Not on this problem at all.
I know not this problem,
But is just in general, where does it come in?
Yeah, I mean, the homework and everything, we weren't given any exam or any problems where we had to be forced to find H to N.
I think it is in the homework, actually. So what, well, there might have been a way to work around it. But basically, I'll just recall for you really quick that if you take this generating function, 1 over 1 minus x to the k, that is the generating function for, this is what I did in class. Turns out that's the generating function for the following sequence, Hn, namely n plus k minus 1, choose k minus 1. So, and this expression here is the number of solutions to a stars and bars problem where you have n stars and k minus 1 bars. So that's the context in which it came up in class, basically. So it's a good thing to kind of try to remember, but you can always rederive it by starting from 1 over 1 minus x, which we already know generates that sequence, Hn always equals to 1. And what you can do, if you call that g of x, is you can start taking derivatives. Okay? So if you take, just to remind you, if you take one derivative of this, you'll get 1 over 1 minus x squared. And on the other hand, if you take the derivative of the power series expansion of this, you'll get 1 plus 2x plus 3x squared. So I'm just taking the derivative of our standard 1 plus x. Here.
Yeah.
I'm just taking the derivative of our original 1 plus x plus x plus x cubed and so on. And so in this case, now you've got h sub n is equal to n plus 1, right? So this is the case where k is equal to 2. So if you put in 2 for k right here, right? What are the coefficients of this power series? They are exactly n plus 1, choose 1, which is just n plus 1. Right? And then if I do it again, I can take another derivative.
What about the negative?
It cancels out. Yeah. So, yeah, you can just, the negative actually keeps canceling out when you take the derivatives. So if you take another derivative, right, then you're going to get this expression, and that just means you're taking another derivative of this power series, which means, and I'm going to not simplify it as I go, so the derivative of 2x is just 2, so I'm going to write it as 1 times 2. Actually, let me write it as 2 times 1, actually. Okay, and then taking the derivative of this, I get 3 times 2 times x. And the next term over will be 4 times 3 times x squared. And so what you'll notice here is that this one, the formula for Hn is actually n plus 1 times n plus 2. However, of course, that doesn't quite match with this because I've got a 1 on top here, whereas over here I have a 2 on top. So you can divide through by 2. So if you divide through by 2, you'll get 1 over 1 minus x cubed equals, basically this whole thing over 2. And your h sub n for that, then, your new coefficients are n plus 1 times n plus 2 over 2. And that's what you get if you plug in k equals 3 over there. What do you get? You get n plus 2, choose 2, which is exactly that number. So, and you can just keep deriving by taking more and more derivatives. You can just keep deriving more and more things here. Is that kind of what you needed to hear?
Yeah. In class, you just went from function for each of n is equal to that, and then this.
Oh, I didn't do all these derivatives.
Yeah.
Yeah.
So I'm extremely confused.
Oh, I'm sorry. Yeah, no, it's just a matter of taking derivatives of the original 1 over 1 minus x. Yeah, Laura?
Maybe it's just me, but I don't remember going back to the series and then finding a formula for each of them.
Okay, that's what she's saying. That's what she's saying.
Right.
Yeah.
We didn't.
I don't remember doing that again.
And then
Okay,
you
I made a table where I just sort of said, all right, so if you have this generating function, then here are the coefficients. And I didn't derive each one of those, and it was in that. I derived a couple of them, I think, but then I didn't derive all of them. So, but everything that's over here,
Yeah, everything was over there we did, but we weren't forced to get down to solving that each of them was equal to n plus 1.
oh, okay.
So,
We didn't do those steps over there.
yeah.
This stuff?
We didn't do that.
So we just came up with the generating function. Okay,
No,
okay.
there were examples like that.
That I did?
Yeah,
On the homework.
or
We had to
in
solve
class. I mean, I have the notes,
Yeah,
so.
you-
You know, it's possible, this is the thing, it's possible that I might have had an example that I ran out of time in one class and just didn't. I'm not sure, it's hard for me to sometimes remember, and some people are going to like my 4 o'clock class one day and my 5:30 class the next day, and so that it's not perfect, right? Like exactly how far I get depends on, you know, how many questions are coming up and stuff. But I don't think that's what's on what is on this board here is anything very too crazy, right? You just take this thing, rewrite it like this, and just say, what are all the coefficients? Well, they're all equal to 1. So, that's basically the idea. Is this looking, is it just me, or are we on the same page on this? Kind of? Okay, let me do another example then. I thought I did one where we had fruit, and I said, yeah.
That was the
for
one.
an example, and I think I'm sure I did it in both classes. Yeah, that you had to do this. You had to do this entire process for that.
So I guess that I just missed the part of you solving for each of n.
Okay.
Which is equal to n in our example.
Well, yeah, like here, there's like nothing that, you're not really even solving for each event. You're just looking at saying, oh, it's 1, 1, 1, 1, 1. You're just looking at what are the numbers in front of these different x's. That's all you have to do. On some of these, it's a little trickier, as you can see, but I know these were in the homework too, because there was that one where I think you had to derive like the generating function for n cubed or something. Like you had to basically use these tools here. All right, can I go on? We okay? All right, let's try this one. Number 4. What is the coefficient of x to the 12th in the following expression? Let's take g of x equals x cubed over 1 plus 4x quantity squared. So why would anybody ever want to solve a problem like that? Well, what if I'm asking you how many ways there are to get 12 pieces of fruit, right? With some conditions, and you write down the generating function. Let's suppose that you write down a generating function, you simplify all the algebra, and it comes out to that. See, this one it simplified out to something really nice, so we were able to immediately write down the answer. But what if h sub n had this as its generating function? Well, then if I asked you, well, what is h sub 12, then you've got to be able to tell me the 12th coefficient. Here it's easy. 1, 1, 1, 1, 1, well, they're all 1. But over here, well, what is the 12th coefficient of that? Might not be as obvious. Do you see what I'm talking about? Okay, so how am I going to figure that out? How am I going to figure out the coefficient of x to the 12th in that rational expression? Maybe, but
1 over 1 plus 1.
Okay, baby steps is what I would do too. So instead of x cubed, let's just forget the x cubed and take it out and look for the coefficient of x to the 9th in the remainder of the expression. So the solution is, this is the same as the coefficient of x to the 9th in a slightly different function, I'll call it f of x, equals 1 over 1 plus 4x quantity squared. Okay? Does that make sense so far? Because whatever the coefficient of x, basically this is x cubed times this thing. So the point is, if I can find the coefficient of x to the 9th in the bracketed part, this x cubed will power it up so that it's x to the 12th. So we just need to find the coefficient of x to the 9th in this expression. Does anybody have an idea how to do that? It's a tweaked version of 1 over 1 minus x. And that's what you have to recognize. Okay, it's instead of 1 minus x, it's 1 plus 4x, and then it's being squared. But we've already kind of talked about how to get a square on the bottom. So this should give us some clues as to which tools we need to use to get that function. Lisa?
We can rewrite the inside as 1 minus negative 4x.
Mm-hmm. Yeah, so the inside of this is 1 minus negative 4x, so it's looks more like 1 over 1 minus x. That's good. And what else can we do? I'm not going to do an extra step for that, but yeah, basically that 4 is like a negative. I mean, does anybody know what this actually is as an expansion?
It
That.
looks like g prime if you replace x with negative 4x.
Right, so when I said, does anybody know what this is as an expansion, the answer I was hoping to get from you all is no, I don't know what it is, because I don't know what it is either, right? We don't know what this one is directly, so let's figure it out from something easier. Okay, so let's start with, we do know that 1 over 1 plus 4x, and this is what you were looking at, Mark, I think, is that if I start from this one and take the derivative, I'll get that one. But let's just take it baby steps here. This is 1 over 1 plus 4x. So 1 minus 4x plus 4x quantity squared minus 4x quantity cubed plus dot, 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 dot. Okay, so that's what it would be. So when I said, does anybody know what the coefficients of this power series expansion are, the right answer to give me for that question is, no, I don't know what they are. But then if I ask you the same thing for this one, and I say, do you know what the coefficients of the expansion of 1 over 1 plus 4x are, the answer now, I hope, for most of us in the room would be, yes, I do know what that is, because it's basically just this expression here. Okay, now this is not what we want. We actually want to get the squared power on the bottom. So what would you suggest that I do? Say it louder. Exactly, take the derivative of both sides. If it worked here, if this worked and it gave me the squared power on the bottom here, it should hopefully do that over there. Now I admit, we're probably going to get a factor of 4 that flies out of here that we don't really want, but we can fix that later. Okay, so for now, let's just go ahead and take the derivative of both sides. So take derivative. We've done these before, right? We've seen examples. We take derivatives, and back on the quiz, I think I made you take an integral at one point. Okay, so the derivative of this one, yeah, I'm going to just use the quotient rule. So the low squared goes on the bottom. Remember I made a joke in class that you have to actually know calculus to do combinatorics? So the quotient rule, the denominator squared, then we have low d high is 0, minus the top times the derivative of the bottom, so minus 4. low, d high minus high, d low, negative 4 over 1 plus 4x quantity squared. And that is equal to, I take the derivative of both sides. So I have negative 4 here. On this one, I'm going to write it as actually 4 squared times 2x. And here I'm going to write minus 4 cubed times 3x squared. See, I don't like to simplify the constants because I like to see the patterns better. And so on and so forth, right? So I get that. Remember, we are trying to find the coefficient of x to the 9th in this expression. I bet we could figure out the coefficient of x to the 9th in this expression. It's not quite what we want because this is the negative 4 in front here. So, but we can get what we want. We can get what we want out of it. Sorry, Joseph. Keeping my cameraman busy. Pardon?
Can we just divide by negative 4?
Yep, that's exactly what we're going to do. We're going to divide by negative 4. So divide by negative 4. Guys, the thing about this is you don't have to see all of the steps right when you start the problem. You just have to recognize that, okay, this is the denominator I want to get. I basically am going to have to take a derivative and I'm going to have to modify 1 over 1 minus x. If you can figure that part out, you'll be able to do this. The first part is to just change 1 over 1 minus x to 1 over 1 plus 4x. Just write out what it is. To get the squared on the bottom, we take the derivative of both sides. Yes, it introduces an unwanted numerator, but we can fix that later. We don't have to try and solve it all in our head right at one moment. So let's divide by negative 4, and now we get 1 over 1 plus 4x quantity squared is equal to, what is it, 1 minus 4 times 2x. I'm switching the signs on these terms, right? Plus 4 squared times 3x squared. And the next one would be minus 4 cubed times 4x cubed, and so on, right? So if I went all the way to x to the 9th, what would it be? X to the 9th here, let's see, this is 4, you just have to look at the pattern, right? X to the 9th, I'm going to have, first of all, it's going to be a negative, right? Because the odd powers are being subtracted. How many powers of 4 will I have out in the front of everything? 9, right? Because this exponent agrees with the power of x, right? And then what will be the coefficient? If I have an x to the 9th, what would be the constant right in front of that? 10, right? There's the answer. Just like that. Jeff.
Can you just think of this multiplying 1 over 1 plus 4x times itself?
Yeah. You can do that too. The problem with that is then, of course, in terms of answering the question, you have to literally like foil, kind of in your mind, figure out, you're going to foil this with itself, right? And you're going to look for the coefficient of x to the 9th. So, I mean, there'd be a lot of cross terms, right? You have so the constant term times the x to the 9th term. Then you'd have the x term times the x to the 8th term. And you'd have a bunch of those terms.
It just becomes 4 to the 9th, 4 to the 9th, 4 to the 9th, or negative 4 to the 9th, negative 4 to the 9th, negative 4 to the 9th.
Yeah, you can do it that way. I mean, you'll figure out, well, how many of those are there? Well, there's 10 of them. Okay, and that's fine. I don't mind that. It's just, I like to sometimes think of just more of like, what if you didn't see that? Or you didn't want to do that kind of mental arithmetic. This is it. What are you going to do if I give you one and I have a denominator that's got like a, you know, I don't know, 1 plus 4x cubed on it? Say again? Yeah, you're going to have to take yet another derivative, right? And that'll get you the right denominator. You might have to tweak the numerator a little bit, but it will get you the right denominator. Okay? Did you have a question, Joseph?
Yeah, I was saying alternatively, couldn't we just say like y equals negative 4x and then plug that into our handy g of x equation right there and then just pull the constant out of that and raise it to the power we're looking for?
Yeah, you can also tweak this expression too. Exactly. You know what value of k you want. You just have to replace x with the right thing. Yeah. Lots of ways to do this. Okay, you guys comfortable with that stuff? Okay, let's go on to something else. I'm spending a little more time on the earlier stuff. You probably noticed that. That's on purpose because I think the graph theory is more fresh in our minds. So I'd rather focus on the things we need more help with. So let's try another one. This is problem number 5. Prove that 5 divides the 5n Fibonacci number for all n greater than or equal to 1. Sound familiar? Guys, okay. How are you going to prove it? I'm going to tell you in a minute, but how are you going to do it first? Yeah, anytime you're proving for all positive numbers some fact, induction is a reasonable thing to think of. I mean, you don't have to use induction every time you see something like this, but it's a great bet here. So let's try it. If I'm going to do induction, what's the first thing I need to do? Base case. Mark, what is my base case value? 1, exactly. N equals 1. Now actually, the number of base cases that you need depends on the details of the proof. So once you do the induction step, you have to look and see, am I only using the previous version of the statement to prove the current version, or am I using lots of older versions? And I may have to go back and do more base cases later. We'll see. So is it true that 5 divides f sub 5? Better be. What is f sub 5 anyway? So how does this start? f0 is 0, f1 is 1, f2 is 1, f3 is 2, f4 is 3, f5 is 5, right? Great. 5 divides itself. So, by the way, on that, you don't need, please don't waste a lot of time during a test going on and on about that. Just, it's clear, right? Basically, if you wrote clear on this, I would be totally fine with that. I know, you don't get to say that very often, but on that you probably could. Okay, let's do the induction step. So what am I going to assume here?
Assume 2 for n.
I'm going to assume that I'm going to do it the way I like to do induction, which is not the same way everybody does it. But that is, I'm going to assume that it's true for the n-1 version of the statement. So I'm going to assume that 5 divides f sub n minus 5. Does everybody see where I got 5n minus 5 from? I replaced n with n minus 1 and just simplified it. So I'm just going to assume that. Okay? And then we need to show that 5 divides f of 5n. Okay. So this is where we are at. Anybody have any ideas what I can do?
Start with f sub 5n.
Okay. What do you want to do with that? See, okay. Oh, I think I know what you want to do, but I'm going to jump in here already because I'm too excited. I need to use my assumption about what 5 already divides. And in order to use that assumption, I've got to take the number I'm currently trying to say something about and figure out how to write it in terms of the number I already know something about. So Joseph, I'll let you take over again. I'm sorry, I didn't mean to catch you off.
Oh, well, from the basic second order recurrence to Fibonacci's, we know f sub 5n is equal to f sub 5n minus 1 plus f sub 5n minus 2.
Very good. That's just the recurrence relation for the Fibonacci numbers, right? By the way, as far as Fibonacci numbers go, I do expect you guys should know what they are. You should know what the terms are. You should even know the general formula for f sub n, the thing with the square root of 5 in it. Just, or be able to derive it. And you need to know the recurrence relation. This is the recurrence relation. Does this by itself help us? doesn't have the right number in it, because we need to get this number involved in it. So, is Joseph giving us bad advice, or is he
Yes.
going in the right direction? Jason, what do you think?
Just do it again for that, and then so 5 and minus 1.
Exactly, we can just do it again for this guy, right? I think we did something like this on the homework. So I do it again, and what'll happen is, you'll get another one of these, so you'll have 2 of those. So 2 factors of 5n minus 2 for f, and then the f of 5n minus 3. Great idea. Now, does that get us what we want? No, so what are we going to do? Do it again. Anthony, what am I going to get?
3 f sub 5n minus 3.
Okay.
And plus 2 f sub 5n minus 3.
Yeah. You weren't getting help with that, were you? No. So this f of 5n minus 2, you just write it as f of 5n minus 3 plus f of 5n minus 4, and then you combine. I'm just trying to do this quickly. If you're on a test, you can write it all out and just do some algebra to simplify it. I'm just not writing all the steps. Yeah, Lisa?
Are these coefficients gonna be related to the actual construction numbers?
You know they are. This is actually an amazing thing. The Fibonacci numbers themselves start showing up as the coefficients. So what's the next one going to be?
5 f sub n minus 4 plus 3 f sub n minus.
And you mean f sub 5n minus 4, right?
Yes.
And then plus, what's the next thing?
3 f sub n minus
F sub 5n minus, oh, 5.
5.
Okay? What's the next one?
We don't, we just go through
Awesome. Yes, that's right. I was trying to see if everybody knew what we were doing, because we could keep doing this forever. But there is a good place to realize that you don't need to go any further. Take a look here. What are you trying to prove? You're trying to prove that 5 divides this guy, which means you're trying to prove that 5 divides all of this. What do you already know? 5 already divides this piece by assumption. And what about this piece? Has a 5 there, right? So it must divide it. So this is equal to, what we could do to make this more precise is we could say, if, well, let me come over here so I have a little more room. Okay, so if we write f sub 5n minus 5, see, we assumed here that it is divisible by 5, so I can write it as like 5 times k for some k. For some integer k. Then f of 5n itself is actually going to be 5 times f of 5n minus 4 plus 3 times k. So here's the 3, and the 5n minus 5 has been replaced with 5k, and I pulled the 5 part out already. See that? Why did I want to write it like this? I see the 5 is factored out there, right? So that means 5 divides f of 5n, and we're done. Okay? There's a little bit of baby number theory in there, just divisibility properties of numbers and such, but nothing too heavy. Okay. All right, are we good on that? Okay. I've done a few examples of each thing. You know, you guys, as we're going along here, the idea of the review session isn't, oh, when we're done with the review, we're ready for the test. The idea of the review session is, oh, we're done with the review, now I know what we need to go focus on. Okay, so I've kind of done all of the non-graph theory, at least 1 or 2 questions from each of the non-graph theory things. I'd like to do a little graph theory, okay?